This is problem 13-125. As the car shown in the figure below moves along the circular road, its speed increases uniformly from velocity A equal to 30 miles per hour at location A to velocity B equal to 60 miles per hour at location B. Determine the magnitude of the car's acceleration when S equals 300 feet. Okay, so what is important about this problem and this section is the fact that the motion is circular, okay? Meaning it has the same motion as an orbit around a planet, a circular orbit around a planet. And if we remember from Physics 170, if there is circular motion, you can have, especially if it's an orbital motion, you can have a change in velocity with only a change in direction, okay? And so that is what we call centripetal acceleration, where the acceleration is only pointed inward, but that's not the case here. I just want to point this out because the car is moving at a slow velocity in the beginning and a faster velocity at the end. So that means that there is acceleration both for changing the direction of the car, so making the car turn, and also making the car increase speed. Okay, so there are going to be two accelerations here that we have to take into consideration. All right, and because of that, that's why we're going to be dealing with normal and tangential kinematics. Right, now remember, kinematics meaning motion only. We don't know what's causing the change in velocity, what's causing the acceleration both in the car's speed, but also causing the car to accelerate by turning. We are only told about how the car is moving, not what is causing the car to move. And what is causing the car to move, the forces, whether it's the friction on the wheels to the ground or the engine, will be in the next section with kinetics. So knowing that we only care about the motion, or only know about just the motion, they give us the velocity values, they give us the positions, okay, and they're asking us to figure out the magnitude of the car's acceleration. And then, because this is circular motion, we are going to talk about the acceleration in two different ways, basically two different directions. The tangential acceleration, okay, and then the normal acceleration. And what we mean by normal acceleration is normal to the circle. All right, let me redraw this in a little bit better fashion. So we have the tangential acceleration, which is tangent to this path, this circular motion. And then we have the normal acceleration, which is normal to the circular path, okay? And these two terms are talked about in the textbook. And let me introduce you to the two functions that will have the scalar values that we need to find that you need to be concerned with when it comes to the velocity and the acceleration. So the first equation or function that the textbook discusses is the velocity equation. And when we're talking about the velocity equation, we care about, when dealing with the normal and tangential coordinates, we care about the normal and tangential vectors, the unit vectors, when it comes to the path. So for this first diagram, figure 13-27, they are talking about a position. So that's why S of t, they're using S as a position. And you can see the normal and tangential coordinate system, the position of the particle is specified by giving the distance as it moves along the path. So this red line is the path. And at the two locations that they are highlighting, here and here, there is a normal and a tangential component. And at the other direction, there is a normal and tangential component. Okay? And then if you do your derivation, so this is the definition of a derivative, then you will end up with this vector here that is showing that the particle will be moving tangential to its path. And hopefully that is not shocking, okay? Take a second to think about if the object is moving in this particular path and it goes from this location to, say, this instantaneous, it's not instantaneously moving to those locations, but let's say it's just going from this highlighted location to this highlighted location. It can only move tangential to its path that we are basically drawing out. We're predicting the future, more or less, and so every instantaneous moment of motion that this particle moves along has to be tangential to its path of motion. That's basically what the tangential is. Okay, so this is hopefully not a shocking form of the velocity function. Now here on this page 61, they are doing some derivations using the definition of a derivative and working our way through the derivative derivation. And what I want to highlight, what I want you to take home is this function here, okay? This is the function for the acceleration in a tangential and normal coordinate system, okay? So what is of importance is the scalar terms that are used in this function. So in the final form of equation 13-25, we'll have a v dot, which is a scalar linear acceleration. It's the derivative of the velocity, the linear velocity, okay? And then we also have the scalar of the velocity, okay, not v dot, just v squared, and then rho. Now, what is rho? Rho is this distance right here. If we have a path, an instantaneous moment of that path, okay, there's a lot going on here in this diagram. So if the red line is the path that the particle has and will travel, then what they are doing in this diagram is picking a specific location in that path. And so if you are to say, I care about the particle's position at this time, at this location that I just drew a dot, then there is a tangential trajectory. And therefore, that implies that if there's a tangential trajectory, that means that there is a circular curve that passes through that point and only that point. Okay, so if that circular curve at that location of the particle's path has a radius of curvature. So if I have a circle, I'm just going to draw an arbitrary circle. Okay, this has nothing to do with the figure. And there is a radius, then that means that the radius of curvature could be thought of as just a radius that represents a curve that would complete an entire circle that would have that radius. If I was to extend the radius of curvature, then the curve would have to be bigger in order to come all the way around and have that radius. So that means that the first radius that I drew would be here. The radius of curvature would match that radius, come around, and would make a circle. Okay, so that's what rho is. Rho is this symbol, and it is representing a radius of curvature that if you were to continue the circle all the way around, that circle would have that radius. And where did that circle come from? That circle came from the tangential value at the location of the particle's path at that moment. Okay, that was probably a lot to take in. And that was just to talk about the rho, right? Really, what we care about is we care about these scalar values. We want to be able to find those scalar values. They will be associated with the two unit vectors, the tangential unit vector E sub t and the tangential or the normal unit vector E sub n. And that is the most important form of the function that is to give us the acceleration of the particle at any moment in time using normal and tangential coordinates. Okay, so let's go back to the problem now. All right, quick recap. We have a car. They give us this distance. They say that the car is driving along a circular road. So this 600 feet, that is the rho. That's the radius of curvature. Okay, and so they start us out at point A. The car has been driving around the surface, around a curve, and then eventually gets to point B. I know point B is actually supposed to be a little further around the corner, but it really doesn't matter. Okay, they tell us that at A, there is a velocity of 30 miles per hour. And then at B, there's a velocity B equal to 60 miles per hour. All right, and they want to determine the magnitude of the car's acceleration when S equals 300 feet. Okay, well, what is S? They are saying that there is a location A, a location B, and somewhere in between is a location S. All right, so we need to figure out what the speed will be at S if S is a curved distance of 300 feet away from A. And the car is going to accelerate smoothly to whatever speed it will be at B, location B. All right, so how are we going to approach this? Well, one thing is that we are told that there is a difference in velocity from 30 to 60, and I guess we have to assume that the acceleration is going to be a constant. So you could think of that the car's acceleration, which is v dot, I'm just putting v dot as, just to remind you that that is also the acceleration, is going to be some constant. Okay. And now we need to figure out some sort of function. Well, one way is we can integrate a acceleration that we know to be constant. So what we can do is we can say, all right, if we integrate some number or some value, then that means that the integration will be v dot t plus some initial velocity. Okay, this is c. All right, that is just your plus c. Okay, well, what is our initial velocity? Our initial velocity is 30 miles per hour, but that's not really the normal units that we use for velocity. So we need to convert that to feet per second. That is 44 feet per second. Okay, so that means that our function has become v dot t plus 44 in feet per second. So this is our velocity function as a function of time. Okay, so we made an assumption that our acceleration function was a function of time, and it was a constant. So therefore, but we don't know the constant, so we just kept it as v dot. This might feel like a cheat. Some people do express it as, well, I can just cheat. I don't know what it is, but I know that it's a function of time, so therefore I will just put a dot over, and I will do the integration, and I'll just multiply a t next to it. Okay, it's completely legit. If you have never really seen that before, trust me, it works. Okay, and then we can do it again. So now we can do our position. I'll do what the book does and call the position S. Okay, and we can integrate again. So I'll just do 44t first, okay, plus v dot again, but this time it's t squared and over 2. Okay, and there's a dot, forgot my dot. Okay, and then it's plus c again, but this time it's plus the initial position. Well, where's the initial position? It's at the beginning. It's 0. All right, so we have a function of the acceleration, which, by the way, is here, a of t, which is just a constant. We don't know the value. That's what we're trying to find. Okay, and then we have our velocity function, and we have our position function, and then here's our acceleration function. All right, so what can we find out of this? Well, we do know that we want to be at a certain location, but now we need to know when. When do we get to that location? Because basically the unknown in all of these is t. All right, well, one of the unknowns is, so let's find out when we are located at 300 feet. So that means we need to set the position function at 300, and then we need to solve for t. However, we still have the v dot problem. Well, then that means that we need to pick a second equation. Well, how about our velocity equation? Our velocity equation also has v dot and it also has t. All right, but we don't know when we get to 300 feet, and I would argue we don't know where A or B is, right? Well, this is one of the reasons why I chose this problem. I feel like it's not incredibly obvious that since the book is saying that this car is riding on a circular road, and it gives you, I'm going to redraw the problem over here on the side, and it gives you that the car has a radius of curvature of 600 feet, and it says A is down here, and it says B is up here. And I at first had drawn the diagram. It's like, oh, I won't draw it just quite perfect because it doesn't matter. However, unfortunately, it does matter, okay? If you look at how the book has the image set up, I find this annoying, but that's why I wanted to show you this problem at a time. There's nothing in the problem that tells you how much of the circle that you're seeing, but they're basically saying, look, this is the bottom of the circle. This instantaneous location here is horizontal. We curve up exactly circular, and then we get to a vertical position at B. So therefore, this is a semicircle. This is a quadrant of the whole circle. All right, well, if A is located at the origin, I didn't put it exactly on there, but if A is down here at the origin, then that means B is exactly 1/4 of the circle up. So we actually do know something about the final location of B, or at least we know how far along this curved path the car has traveled, like how much distance the car has actually changed. How do we know that? Basically, it's the perimeter of the circle divided by 4. So let's do that calculation. So that means that the position at B is the distance traveled from A to B, which is equal to 2 pi diameter of 600, which is the calculation of the circumference of a circle, but now we only want 1/4 of it, so we divide by 4. So this means the car has moved a distance of 942.5 feet. All right, this is the length of travel along the curve of the road. Okay, it's not the straight line distance from A to B. Don't get confused and think that we calculate a straight line distance. We're doing the curve of the car from A to B. All right, this is the distance the car has traveled. All right, and when is this? Well, that's what we're going to find. So I said, hey, let's choose 300 feet, but we don't know the v dot value, and we don't know the velocity at 300 feet. So therefore, we actually have 1, 2, 3 unknowns. So that was not a good location for me to recommend. A better location is location B, up here, because now we know where it is, okay? And we also were told how fast we are going at that time. So now we know 60 miles per hour, okay? And then we only have time and v dot left as unknowns, and we can find those two because then we have two equations, two unknowns. So let's do that calculation. So if we plug in the 60 miles an hour, which by the way is actually 88 feet per second, which is the number we should actually be using, then we'll have 88 equal to 44 plus v dot t at B, and this is all, at location B, okay? And then we'll have the distance of 942.5 feet equal to 44 time at B plus V dot T of B, T at B squared, and then divided by 2. All right, we can solve for V dot and T sub B. All right, well, the time at B is 14.3 seconds, and the V dot is equal to 3.08 feet per second. All right. Okay, so the problem is asking us to determine the magnitude of the car's acceleration when the car is located 300 feet along that curved circular path. All right, well, what did we find? We found the time at B, and we know the distance is going to be 300 feet, and we just found V dot is 3.08. So now we just need the time at the new location, right? But hold on a second, this doesn't make sense because the question is asking us to determine the car's acceleration, and isn't V dot the acceleration? So isn't that the answer? V dot is the derivative of velocity, and that is the acceleration. So therefore, 3.08 is the answer to the question, right? Well, it's the answer to the car's tangential acceleration. When we accelerate around a curve, and if we only care about the change in speed in the direction of travel, then we are usually talking about the acceleration that the engine puts on the car to make the car go forward at every instantaneous location. All right, but the true physics mathematical version of acceleration has to take into account also that the car is turning. So we have found v dot, which is the acceleration of the car, but it's only the tangential. Right? It's how quickly the speed and the direction of motion, the tangential motion, is changing. All right? We need how the car is turning as well. So we've only technically found half of the information. So this is the tangential acceleration. All right? Make sure that you understand that this is not just A as a function of time, the acceleration is a function of time. This is the tangential acceleration as a function of time because of how the car is moving. And this completely requires us to understand the system. Right? It's not just follow the pattern of the math and get the answer. You have to understand what it is you're finding. The acceleration of the car changing speed in the forward direction is always just a tangential acceleration, right? When the car is turning. Okay, so we have to find the normal component to the acceleration. How are we going to find that? Well, go back to the book, look at page 61, okay, of the book. Let me just go ahead and say, so page 61, where I've talked about before. Look at equation 13-25, and I'll write it out for you again. So the total acceleration of point P, so some object is P, moving along some path, okay? The final version that is the most useful is v dot scalar and the tangential unit vector plus the scalar of the velocity squared over the radius of curvature times the unit vector and the normal. So we just need to know these two values. We already found v dot. We found the tangential. All right, that was the 3.08, and now that's E hat T. All right, now we need to find the velocity in the rho. Well, the rho is the 600. So what is the velocity? Well, let's go back. Do we have just the velocity anywhere? Well, we don't have the velocity found at 300 feet, at least not yet, right? So, but we do know the v dot value, and we need to know when we are at 300 feet. How do we find that? Well, let's go back. Do we know enough about the position function? So we definitely know when, or when we know where we want to be, 300 feet. We can find when if we know the v dot value at 300 feet. Well, we did. It was 3.08 feet per second. That was the tangential acceleration when we're at 300 feet. We found that recently. So now we can find when. This is because v dot is a constant. The acceleration, the tangential acceleration, is constant. We were told this. So 3.08 feet per second squared, I forgot to put a squared, is the acceleration, and it's constant. So therefore, we can put this acceleration value in for the position equation even at 300 feet because the acceleration is constant. And now we can solve for t. Well, if we do that, then we end up with t is at 300 feet. So t at 300 feet is equal to 5.67 seconds. All right. Does that make sense? Well, we know b is at 14.3 seconds, and we know that the entire route traveled is 900 feet. And so 300 feet is about 1/3 of the way. Yeah, that makes a little bit of sense. That's about right. Okay, it's a good opportunity to make sure things make sense when you get them. All right, so now if we know when we are at 300 feet, 5.67 seconds, then we can find the velocity at the time that we are at 300 seconds. So if we take the velocity equation, or velocity function, right, and we know that that function is the 44 plus v naught t, and if v naught is 3 dot is 3.08, and the time that we are at 300 feet is 5.67 seconds, then that means the velocity at that particular time is 61.52 feet per second. All right, so then that means we can put that velocity value of 61.52 feet per second into this velocity squared term that is then divided by the radius of curvature and will give us our our normal acceleration. So 61.52 e hat n. All right, that means that our normal acceleration is going to be 6.308 feet per second squared. And just to reconfirm, our tangential acceleration is 3.08 feet per second squared. And then that means that our total acceleration, which is the actual question being asked, is going to be the square root of squares. And that equals 7.02 feet per second squared. All right, they don't ask us for an angle. They just ask us for determine the magnitude of the car's acceleration. But the car's acceleration is going to be, if this is the raised cursor, here's the car. The car's acceleration is not straight tangential. It is slightly over. It's also causing the car to turn. And that's not due to the engine, right? The engine is only doing the tangential acceleration. The wheels are causing the normal acceleration, the friction of the wheels on the road, okay? And together, those two things, the wheels and the engine, are causing a vector of slightly higher than the acceleration due to just the car speeding up of 7.02 feet per second squared.